All right, welcome back to more puzzles with trigonometric sum and difference formulas. So I'd like to do just a little bit of review. Let's talk for a moment about the Cartesian axis again. So if we begin to think about describing angles around and around this coordinate axis. So at this position, we would say the angle formed with the x-axis and that segment that I've been swinging around is 0. And then as we continue to swing this side around, we pass through all sorts of different angles. So let's label some others. There they are labeled in degrees, and now they have been labeled in radians as well. And always remember from this that pi equals 180 degrees. You can form that into a conversion factor and do all sorts of conversions between degrees and radians, but I refer you to chapter 8 in your book for more information on all of this. Please read that. Always remember, check your mode on your calculator. We're going to be using both radians and degrees. Make sure you are in the right one for the problem you are working on at present. Okay, let's do a little bit of application with this stuff. All right, because sometimes these formulas can help to simplify things when you're actually working on things in the field. So for instance, let's say you're studying an oscillating spring. You have a spring that has some weight on it. It's moving up and down. How can you describe that motion? Well, that definitely looks like a formula in need of some simplification. But let's look closer. We have the sine of omega t plus alpha there, and we have the cosine of omega t plus alpha in that position. We also have alpha by itself here and alpha by itself here. Starting to look a little familiar. Let's make it look a little more familiar. Let's go ahead and let p equal that omega t plus alpha and rewrite this as the sine of p times the cosine of alpha minus the cosine of p times the sine of alpha. That looks very familiar. It looks quite similar to this. The sine of alpha cosine beta minus cosine alpha sine beta. In fact, it looks exactly like the formula for the sine of the difference between two angles. So let's go ahead and finish out that formula now that we have identified the pattern. This is equal to the sine of, our alpha in this case is p, and our beta in this case is alpha. Okay, so don't get hung up on the letters. Think about this as the first variable and the second variable. The first and the second. The first and the second. Okay, position matters in these formulas. But are we done? We have simplified it. Let's get rid of the one we don't need right now. We do not have the original variables, so that's what we need to do now. We substituted p for this more complicated expression. Now we need to get back to that expression for our final answer. So we're going to write this as the sine of p is actually omega t plus alpha minus alpha is, well, alpha. We didn't substitute anything for that. But look at what that did. Now we have just omega times t, because alpha minus alpha gives us 0. That's much simpler than the original format. All right, time for another example where we actually put a value in. Since 15 degrees equals, this will be example 2. The oscillating spring was the first example. So since 15 degrees equals 225 degrees minus 210 degrees, we could express the sine of 15 degrees as the sine of 225 degrees minus 210 degrees, In other words, the difference between those two angles. We have a formula for that. So there's the formula in all of its glory. That is the formula for the sine of the difference between two angles. Since I already have these color-coded, let's go ahead and figure out where we would graph them on that Cartesian axis. There's 180 degrees, and each of these would be beyond that. In fact, 225 would be 45 beyond that. So somewhere around there. That would be 225 degrees as a standard angle. So there they are, written as standard angles. And if we subtract 210 from 225, we will find that there is a 15-degree difference between those two. So now we could figure this out with the calculator, but you know about reference angles. So let's see what happens if we look at the reference angles. Okay, for a reference angle, it's always found by dropping a line or raising a line to the x-axis, forming part of a bow tie. And if this is 180 degrees, what is that reference angle? Well, the reference angle is 45 degrees. 180 plus 45 equals 225. And we have a 45-45 right triangle. Careful with these. This is in quadrant 3. So when we are writing the lengths of the sides, we're going in the negative direction for x. We're going in the negative direction for y. Your hypotenuse is always going to be positive. And you should remember that for a 45-degree angle, both the sine and the cosine are the square root of 2 over 2. Remember, this is the reference angle for 225 degrees. So the sine of 225 degrees equals the square root of 2 over 2. And the cosine of 225 equals the square root of 2 over 2. Now let's look at the 210-degree angle. We throw a line up to the x-axis. We form the bottom of a bow tie there, and we can calculate that this angle is equal to 30 degrees. 210 minus 180 is 30 degrees. We have a 30-60 right triangle. The measures of these sides are the side opposite of 30 degrees is always 1, but in this case it's going down, so it's a -1. The hypotenuse is always 2, and the longer side, the side adjacent to 30 degrees, is the square root of 3. However, this is going in the negative x direction, so it's a negative square root of 3. So the sine of 30 degrees is the opposite over the hypotenuse. The cosine of 30 degrees is the adjacent over the hypotenuse. Please remember that the actual angle that has a sine of -1/2, actually there are two of them, but one of them is the one we started with, 210. Okay, and the cosine of 210 is actually what equals the negative square root of 3. So let's substitute that in. The cosine of 210 is negative square root of 3 over 2. The sine of 210 is -1/2. Now you need to indicate that those trigonometric functions were multiplied by each other, but do not lose that subtraction sign that's there. Okay, let's do the multiplication. We have negative square root of 6 over 4 minus, and then we have negative square root of 2 over 4. So we have now a negative times a negative right here. That's going to give us a positive, and we are going to be looking at negative square root of 6 plus square root of 2 over 4 as our final answer. Okay, cool, but let's look at something else. Sometimes you may not be given angles, you may be given trigonometric ratios. And when you're given those, pay close attention, because you want to see if you're given anything about the quadrant information. The answer here is definitely yes. That's a good thing. Let's talk about a couple of other special triangles first. Here's another special triangle. This special triangle is defined by the lengths of the sides. A 3, 4, 5 right triangle. Another special triangle that is defined by its sides. The smallest side is 5, the other side is 12, and the hypotenuse is 13. Let's see what those special triangles have to do with this problem I'm about to give you. So far, I've just given you the setup of the problem. You know that the sine of alpha equals 4 over 5. The cosine of beta equals negative 12/13. Let's graph those. We know that sine is opposite over hypotenuse. So we're looking at this triangle. Okay, and it says it's in quadrant 1, so I'm going to draw that special triangle in quadrant 1. And I'm going to label it a 3, 4, 5 right triangle. Okay, so that's the angle I'm looking at there. And then the cosine of B is in quadrant, okay, B is in quadrant 2 because it says so. We're looking at the cosine. That's adjacent over hypotenuse. So this is negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Negative 12. And then the hypotenuse is 13. We know this side goes out here, but does it go up or down? Well, it's in quadrant 2. So it's going to go up. And the hypotenuse is going to be 13. So if you have memorized this special triangle, and you know this is a length of 12, it's in the negative direction, and you have a hypotenuse of 13, then you have another special triangle. You can go ahead and fill in what's missing. Okay, notice they gave us the 4 and the 5 for alpha. They gave us negative 12 and 13 for beta, and we were able to fill in the other two values because we're familiar with these two special triangles. And if these were not special triangles, we could use the Pythagorean formula. So knowing the sine of alpha and the sine of beta, we were able to draw the complete triangle and label the sides appropriately. Now that we have all those sides labeled, we can work with any of the trigonometric functions we want to. So let's evaluate the tangent of beta minus alpha. Okay, first notice the order switched between beta and alpha. Alpha usually comes first. It doesn't have to. We just have to follow the pattern. The pattern for tangent, since this is the difference between two angles, will be tangent of the first angle, which in this case is beta, minus the tangent of the second angle, which in this case is alpha, divided by 1, change the operation to plus, tan. The tangent of beta times the tangent of alpha. I don't see tangent beta or tangent of alpha written anyplace there, but I do know the sides of those triangles. So looking at each of those triangles, remember we had alpha, it's written in there real small. Let me write it bigger. Alpha goes right in there, okay? That's where alpha is. And beta is here. There's a little more room for beta. Okay, that's this angle. Let's look and see what the tangent of beta actually is there. It is the opposite, which is 5. Length of side is 5. And the adjacent side is negative 12. Now let's find the tangent of alpha. Okay, so let me make this bigger so you can see it easier. The tangent of alpha, in this case, is going to be equal to, here's alpha, opposite over adjacent. Now that we've determined that, let's get back to our formula. We can now say that this is equal to, let's see, tangent of beta we found is 5 over negative 12. Notice I'm not just substituting for the angle. I am substituting for the whole thing. I am substituting for all of tangent beta. And then I have this subtraction sign that's part of my formula. And then I have the tangent of alpha. And once again, I want the whole thing. I'm substituting for the tangent of alpha, and I'm substituting in 4/3. But that's divided by 1 plus the tangent of beta, which is 5/-12, times the tangent of alpha, which is 4/3. And then a whole bunch of arithmetic with fractions gives you -63/16 as your final exact answer. You can evaluate that on a calculator if you wish. Let's do another example of this. Okay, here's another example. If sine of alpha equals 5/13 in quadrant 1. Let's draw that. Okay, sine is opposite over hypotenuse, so we're only going to go up 5 in quadrant 1. We're going to have a big long hypotenuse of 13. So we can calculate the remaining side or remember our special triangle, 5, 12, 13, right triangle. And then we need to draw the next triangle, which is in quadrant 4. This is going to be a little tricky to draw. Sine of the angle always gives you the adjacent side. So that would be here. And that little value there is going to be a 3. Okay, and the hypotenuse is a 5. So we don't have this number. We have the 3, we have the 5. That's a special triangle. So that side's 4. 3, 4, 5, right triangle. We were asked to find the sine of alpha plus beta, so let's write out the formula first. That would be sine alpha cosine beta plus cosine alpha sine beta. And since sine of alpha equals 5/3, every place we see sine of alpha, we will put 5/13. Okay? Nothing else. All right. So now cosine of beta, we've been given. It's 3/5, so everywhere I see cosine of beta, I will put 3/5. Now, do I have cosine alpha listed? No, but I do have my triangle drawn now. Now I can look at this triangle and see that the cosine of alpha equals the adjacent over the hypotenuse. So I can put that in here. Now let me draw the other triangle a little bit bigger so it's easier to see. Quadrant 4, our y value will be -4. 3 and 5 are the sides of 3, 4, 5, right triangle. And I need the sine. Oh, and where's beta? Right in here. So the sine of beta would be the opposite, which is -4 over the hypotenuse, which is 5. These two are multiplied, and these two are multiplied, and right in between them we have an addition sign. It remains there. Okay, so if you do the multiplication, you get 15/65 minus 48/65, which is equal to -33/65. That's as far as you can reduce it. That is the sine of alpha plus beta. All right, one final example here. Simplify this expression. Boy, that could use some simplification. Let's do some color coding, though. Take a look at this. We have the cosine of x plus y, x plus pi, and we have the sine of x plus pi. We also have the cosine of x minus pi and the sine of x minus pi. That looks like here's our alpha, here's our beta. Now, which trigonometric function, which trigonometric sum or difference has the pattern cosine cosine plus sine sine? Well, that would be the cosine of alpha minus beta. Because remember, the sign, the operation is different when you're dealing with cosine. So this is the pattern that I'm thinking about and that I'm recognizing, but my actual answer is going to be the cosine of, because my alpha is a binomial, I'm going to put an extra set of parentheses in here so that I don't make a sign error. That's where my alpha goes. I'm substituting for alpha. I'm going to also substitute for beta, and I'm going to close the parentheses for the cosine. What is beta equal to? Well, I have it right up there. It is x minus pi. Okay? You see, I'm going to have a little bit of sign work to do here. All right, so this is going to be the cosine of x plus pi. I'm going to have to distribute this negative. That's what I meant by sign work. That'll give me a negative x, but it'll give me a positive pi. And then close the cosine there. So this is going to equal the cosine of, well, x minus x is 0, so I only have left here a 2 pi. Cosine of 2 pi. Let's think about that. Where is 2 pi? There's 0, there's pi, and all the way around is 2 pi. Okay, when we're talking about radians. So what is the cosine of 2 pi? That's equal to 1. Remember, if that doesn't quite make sense to you, go back and check out Chapter 8. But that's it. Those are all the examples for this video. We'll talk about this more in Collaborate. See you there.